Imagine discovering that every time someone said light year, they were actually describing something impossible. Not impossible like difficult, impossible like your brain physically refuses to process it. The words roll off the tongue so easily, but hidden inside them is a distance so vast, so incomprehensibly enormous, that once you truly see it, you can never unsee it. The night sky stops being beautiful. It becomes haunting, and you realize we've been alone in ways we never imagined. Are you ready to discover why? Let's begin. Imagine trying to describe every distance in our galaxy using kilometers or miles. You'd be throwing around numbers with so many zeros that conversations would become impossible. Instead of saying, that star is 37,800,000,000,000 kilometers away, you simply say, it's 4 light years away. Suddenly, the universe becomes a little more manageable, at least on paper. Here's something most people never consider. When you look up at the stars tonight, you're not seeing them as they are right now. You're seeing them as they were. You're literally looking back in time. The light that hits your eye left that star years ago, decades ago, sometimes millions or billions of years ago. That light has been traveling through the emptiness of space, crossing unimaginable distances just to reach your retina on this random evening. Think about Proxima Centauri, the closest star to our Sun. It's about 4.24 light-years away. When you see its faint glow in the night sky, you're not seeing Proxima Centauri as it exists right now in this moment. You're seeing what it looked like 4 years and roughly 3 months ago. If Proxima Centauri exploded today, we wouldn't know about it until over 4 years from now. The light carrying that information is still making its way to us, crossing the void at maximum speed, racing toward Earth with news of a cosmic catastrophe. And Proxima Centauri is our neighbor. That's practically next door in cosmic terms. Venture farther and the time travel effect becomes even more staggering. Sirius, the brightest star in our night sky, is about 8.6 light-years away. Betelgeuse, that red supergiant in the constellation Orion, sits roughly 550 light-years from Earth. When you gaze at Betelgeuse, you're seeing light that left that star during the Renaissance here on Earth. Copernicus was proposing that Earth orbited the Sun while that light was beginning its journey to your eyes. Now, before we go further into the cosmic abyss, I want to make sure you're catching every mind-blowing moment. If this is sparking your curiosity about the universe, hit that subscribe button and give this video a thumbs up. Seriously, it helps more than you know, and it keeps me motivated to bring you more cosmic mysteries. Plus, there's so much more coming that you won't want to miss. The light year gives us a framework for understanding structure in the universe. Our Milky Way galaxy, this massive spiral of stars, gas and dust that we call home, spans about 100,000 light-years across. Think about that. If you somehow could travel at light speed, which is impossible for anything with mass, according to Einstein's special relativity, it would still take you 100,000 years to cross from one edge of our galaxy to the other. 100 millennia. Civilizations rise and fall in that time. Species evolve, continents drift, and you'd still be cruising through our galaxy. But wait, it gets even more humbling. The Andromeda Galaxy, our nearest major galactic neighbor, sits approximately 2.5 million light-years away. The light you see from Andromeda left that galaxy before humans existed, before Homo sapiens walked the Earth, before our ancestors even stood fully upright. That photon of light began its journey across intergalactic space while early hominids were still figuring out rudimentary tools, and it's only just now arriving at your telescope or your naked eye on a dark, clear night. This is where the light year becomes more than just a measurement. It transforms into a time machine. Every telescope pointed at the sky is essentially a device for peering into history. Astronomers aren't just observers of space, they're archaeologists of time, digging through layers of cosmic history by looking at increasingly distant objects. The farther you look, the further back you see. The observable universe, the portion of the cosmos where light has had time to reach us since the Big Bang, extends about 46.5 billion light-years in every direction from Earth. Now you might be thinking, wait a second, if the universe is only 13.8 billion years old, how can we see things 46 billion light-years away? Brilliant question. This is where things get beautifully weird. The universe itself has been expanding this entire time. Space itself stretches. So while light from the earliest galaxies has been traveling for 13.8 billion years, those galaxies have been moving away from us the whole time due to cosmic expansion. By the time their ancient light reaches our telescopes, those galaxies are now much, much farther away than they were when they emitted that light. The James Webb Space Telescope, humanity's most powerful eye on the ancient universe, has been capturing images of galaxies that existed just a few 100 million years after the Big Bang. In early 2026, Webb confirmed observations of galaxies whose light has been traveling for over 13.5 billion years. We're seeing these cosmic structures as they appeared when the universe was merely 280 million years old, still in its infancy. These aren't just pretty pictures, they're fossils, frozen moments from the childhood of everything. Understanding light years helps us grasp the sheer scale of cosmic isolation. When we talk about interstellar travel, about sending humans or even probes to other star systems, the light year is the barrier we're up against. Our fastest spacecraft, Voyager 1, launched back in 1977, is currently traveling at about 17 kilometers per second relative to the Sun. That sounds impressive until you do the math. At that speed, it would take Voyager 1 roughly 73,000 years to reach Proxima Centauri if it were headed in that direction, which it's not. Light makes that same journey in 4.24 years. We are cosmically slow. This brings us to one of the most profound realizations in all of science. We are stuck, not just on Earth, though there's that too. We're stuck in our little corner of the Milky Way. Even if we somehow invented a spacecraft that could travel at 10% the speed of light, which would require technology so far beyond our current capabilities, it might as well be magic. A journey to Proxima Centauri would still take over 40 years. A round trip? Over 80 years. That's an entire human lifetime just to visit the closest star. But here's where perspective shifts everything. We feel small when we confront these distances. Insignificant. Like cosmic dust floating in an uncaring void. But flip that feeling around for a moment. We are part of this. You, sitting there right now, are made of atoms forged inside stars that died billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you're breathing, all of it was created in the nuclear furnaces of ancient stars or in the catastrophic explosions that ended their lives. You are literally stardust, not metaphorically, literally. Every single atom in your body, except for hydrogen, was manufactured inside a star. Speaking of connections across space and time, if you found the concept of light's journey fascinating, you absolutely need to check out my video called "The Speed of Light Isn't What You Think." I dive deep into why light moves at the speed it does, what it means for causality and the structure of reality, and some mind-bending implications that most people never consider. It pairs perfectly with understanding light years. The link is in the description and pinned on the comments. Now let's talk about how astronomers actually use light years in practice. When you hear that the Andromeda Galaxy is 2.5 million light years away, that measurement comes from decades of painstaking observation and calculation. Astronomers use several methods to measure cosmic distances, and each method has its limitations and its ideal range. For nearby stars, they use parallax, observing how a star's position appears to shift against the background of more distant stars as Earth orbits the Sun. It's the same effect you see when you hold your thumb up at arm's length and close one eye, then the other. Your thumb appears to jump. The closer your thumb, the bigger the jump. Stars do the same thing, just on a vastly smaller scale. Parallax works beautifully for stars within a few hundred light years. Beyond that, the shift becomes too tiny to measure accurately, even with our best instruments. So astronomers developed the cosmic distance ladder, a series of overlapping measurement techniques that let us reach farther and farther into space. Cepheid variable stars, which pulse with regular brightness, serve as standard candles. By measuring how bright they appear versus how bright they actually are, we can calculate distance. Type Ia supernovae, exploding white dwarf stars with predictable peak brightness, extend our reach even further into the realm of billions of light-years. Each rung on this ladder depends on the accuracy of the ones below it. Get something wrong early on and errors propagate upward, throwing off measurements across the entire universe. This is why astronomers continuously refine their distance measurements using new telescopes, better instruments, and improved mathematical models. The light year itself remains constant, defined precisely by the speed of light and the length of a year. But our measurements of how many light years away something sits, those improve year after year. There's something poetic about using light itself as our ruler. Light is universal. It behaves the same way everywhere in the cosmos as far as we can tell. The speed of light in a vacuum is a fundamental constant of nature woven into the fabric of reality itself. Einstein's special relativity revealed that nothing with mass can reach or exceed this speed. Light sets the ultimate speed limit because it has no mass. Photons, the particles of light, zip through space at maximum velocity, unimpeded by inertia. This speed limit has massive implications for our understanding of causality and the structure of space-time itself. If information could travel faster than light, it could theoretically arrive before it was sent, at least from certain reference frames. Cause and effect would break down. The universe would stop making sense. So light speed isn't just fast, it's the cosmic speed limit that keeps reality coherent and logical. When we measure distances in light years, we're measuring them against this fundamental boundary of existence. Einstein's special relativity, published in 1905, revealed something even stranger about light and time. As you approach the speed of light, time itself slows down for you relative to someone who's stationary. This isn't science fiction, it's verified physics. Atomic clocks flown on airplanes tick slightly slower than identical clocks left on the ground. Particles accelerated to near-light speeds in particle colliders live longer than they should because time dilates for them. If you could somehow board a spacecraft traveling at 99% the speed of light and journey to a star 10 light-years away, you'd experience the trip as lasting about a year and a half due to time dilation. But when you returned home, roughly 20 years would have passed on Earth. Light years aren't just distances, they're intimately connected to the nature of time itself. Let's venture to the edge of what we can observe. The cosmic microwave background radiation, often called the CMB, is the afterglow of the Big Bang. About 380,000 years after the universe began, it cooled enough for atoms to form. Before that moment, the cosmos was an opaque plasma, light scattering off free electrons in every direction. Once atoms formed, light could finally travel freely. That first light, stretched by 13.8 billion years of cosmic expansion, now bathes the entire universe in microwave radiation. When we detect the CMB, we're observing light that has been traveling for almost the entire age of the universe. We're seeing the baby picture of existence itself. the galaxies that emitted the CMB light we detect today are now roughly 46 billion light-years away due to expansion. This creates a horizon beyond which we cannot see, not because light isn't there, but because it hasn't had time to reach us yet. The universe might extend far beyond this horizon. It might even be infinite. But the observable universe, defined by light's travel time since the Big Bang, has an edge, a boundary set not by walls or barriers, but by time and distance. Light years define that boundary. Here's a thought experiment that really drives this home. Imagine you had a telescope powerful enough to see an exoplanet 40 light-years away with perfect clarity. You point it at this distant world and you observe a civilization, structures, cities, technology. But remember, you're not watching them live. You're watching their past unfold. What you see is what that planet looked like 40 years ago. If they're looking back at us with an equally powerful telescope, they're seeing Earth as it was 40 years ago, the year 1986. Chernobyl just melted down. The Challenger space shuttle disaster happened. The internet barely existed. That's the Earth they see. We're both trapped in each other's past, separated by light years of space and decades of time. Now scale that up. Galaxies billions of light years away? We're seeing them as they were billions of years ago, when the universe was younger, when different physical processes dominated, when the first stars were just beginning to light up the darkness. Some of those galaxies might not even exist anymore. They could have collided with other galaxies, been ripped apart by tidal forces, or undergone dramatic transformations. But their light, their ancient light, is only now reaching our instruments, delivering news from an era long gone. This is why astronomy is unique among the sciences. We can directly observe the past. A biologist can't watch dinosaurs. A historian can't see ancient Rome as it actually was. But an astronomer pointing a telescope at a distant galaxy billions of light years away is literally observing the ancient universe. The light arriving at the detector is a messenger from the past, carrying information encoded in its wavelength, intensity, and spectrum. By analyzing this light, astronomers reconstruct what conditions were like in the early universe, how galaxies formed and evolved, and how the cosmos changed over billions of years. The Hubble Space Telescope, launched in 1990, revolutionized our ability to peer deep into cosmic time. Hubble's deep-field images, created by pointing the telescope at seemingly empty patches of sky and collecting light for days, revealed thousands of galaxies, many of them over 10 billion light-years away. Each tiny smudge of light in those images is an entire galaxy containing hundreds of billions of stars, seen as it existed when the universe was just a fraction of its current age. Hubble showed us that wherever we look, no matter how empty a region seems, galaxies fill the depths, stretching back through time. The James Webb Space Telescope, which began science operations in 2022, pushes even further. Webb's infrared vision allows it to detect light from the very first galaxies, born just a few 100 million years after the Big Bang. These galaxies are so distant, their light has been traveling for over 13 billion years. By the time that light reaches Webb's mirrors, it's been stretched by cosmic expansion into the infrared portion of the spectrum. Without infrared detectors, we'd be blind to these ancient beacons. Webb is revealing a universe we've never seen before, answering questions about how the first stars ignited, how galaxies grew, and what the infant cosmos actually looked like. Every discovery pushes our understanding of light years further. In January of 2026, astronomers using Webb reported observing a galaxy designated as having a redshift beyond 14, meaning we're seeing it as it appeared roughly 280 million years after the Big Bang. The light from this galaxy has been traveling through space for over 13.5 billion years. Think about that journey. That light departed its source when the universe was still forming its first large structures. It crossed the expanding void, passing through clouds of gas, skirting around gravitational fields, riding the stretching fabric of space-time itself. And after all that time, after all those light years, it entered the gold-coated mirrors of the James Webb Space Telescope, was focused onto detectors, converted into data, transmitted to Earth, and analyzed by human scientists trying to understand their origin. We are witnesses to cosmic history on a scale that would have seemed impossible just a century ago. And the unit that makes all of this comprehensible, the light year, bridges the gap between human understanding and the vast scales of the universe. Without it, we'd be drowning in incomprehensible numbers. With it, we can grasp, even if just barely, the immense theater of space and time we inhabit. Let's bring this closer to home for a moment. Our own galaxy, the Milky Way, is a barred spiral galaxy containing somewhere between 100 billion and 400 billion stars. The exact count remains uncertain because large portions of the galaxy are obscured by dust, and counting every faint red dwarf is challenging. The Milky Way stretches approximately 100,000 light-years from edge to edge, though recent measurements suggest the diameter might be closer to 87,000 light-years depending on how you define the edge. The disk itself is relatively thin, only about 1,000 light-years thick in most places, though it bulges to around 10,000 light-years thick at the central core. Our solar system resides about 26,000 light-years from the galactic center, roughly halfway out along one of the spiral arms. We orbit the center of the galaxy at around 220 kilometers per second, which sounds fast, but at that speed it still takes us approximately 225 to 250 million years to complete one full orbit. The last time Earth was in this same position relative to the galactic center, dinosaurs were just beginning to dominate the planet. One galactic year from now, if humanity or any of our descendants are still around, we'll occupy this same cosmic address again, having circled the galaxy exactly once. Within our galaxy, thousands of confirmed exoplanets orbit other stars. As of early 2026, we've discovered over 6,000 planets beyond our solar system, with thousands more candidates awaiting confirmation. These worlds range from scorching hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, to frigid ice giants in the outer reaches of their systems, to rocky planets that might, just might, harbor conditions suitable for life. Most of these exoplanets lie within a few thousand light-years of Earth, simply because those are the stars we can observe most easily. The nearest confirmed exoplanet, Proxima Centauri b, orbits our closest stellar neighbor at a distance of 4.24 light-years. Proxima Centauri b is fascinating because it sits within the habitable zone of its star, the region where temperatures might allow liquid water to exist on a planet's surface. But here's the catch. Even though it's our closest exoplanet neighbor, even though light takes just over 4 years to cross that gap, it might as well be on the other side of the universe for practical purposes. With our current technology, sending even a tiny probe to Proxima Centauri would take tens of thousands of years. Breakthrough Starshot, an initiative proposed to send miniature light sail probes to Alpha Centauri, aims to reach speeds of about 20% the speed of light. If successful, the journey would still take roughly 20 years, with another 4 years for the data to return to Earth. That's a generation-long mission to reach our closest neighbor. This is the tyranny of the light year. Space is so vast, and light speed is the ultimate barrier, so even our immediate cosmic neighborhood remains effectively inaccessible. We can observe exoplanets. We can analyze their atmospheres using spectroscopy as their light passes through our instruments. We can determine their mass, their radius, their orbital characteristics. But visiting them, that's a challenge that might require technologies we can barely imagine. or patience measured in centuries. Yet despite these limitations, we continue to push outward in understanding. The TRAPPIST-1 system, located about 40 light-years away, contains 7 Earth-sized planets, 3 of which orbit within the habitable zone. When astronomers discovered this system in 2017, it ignited imaginations worldwide. 7 worlds relatively nearby in cosmic terms, potentially harboring conditions for life. But that relatively nearby still means the light we see from TRAPPIST-1 left that system around 1986. Any signals we send would take 40 years to arrive, and if someone responded immediately, we wouldn't hear back for another 40 years. An 80-year minimum conversation delay. That's longer than most human lifetimes. The light year forces us to confront uncomfortable truths about our cosmic isolation. The universe teems with worlds. Billions upon billions of planets orbit stars throughout the galaxy and beyond. Statistical models suggest that nearly every star hosts at least one planet. Some of those planets must be similar to Earth. Some must have liquid water, stable climates, and the chemistry necessary for life. The numbers are overwhelming. The universe should be full of life, and yet we're separated from all of it by light years. Even if intelligent civilizations exist around nearby stars, even if they're looking back at us right now, meaningful communication would unfold over generations. Consider the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950, "Where is everybody?" If the galaxy is so old, roughly 13.6 billion years, and if life is relatively common, then why haven't we detected any signs of other civilizations? Why haven't they visited us? Why is the sky silent? One possible answer lies in the light year itself. Space is simply too vast. Even advanced civilizations capable of near light speed travel would find crossing thousands of light years prohibitively difficult. The galaxy might be full of life, each civilization trapped in its own bubble of space-time, unable to reach across the distances that separate them. Or perhaps we're early. The universe is only 13.8 billion years old, which sounds ancient, but stars can continue forming for trillions of years into the future. Most of the stars that will ever exist haven't been born yet. Maybe we're among the first intelligent species to arise, looking out at a cosmos that will eventually fill with civilizations, but not yet. Not for millions or billions of years. From this perspective, our loneliness isn't a paradox, it's a consequence of timing. We're pioneers whether we intended to be or not. The light year also helps us understand the remnants of cosmic violence. When massive stars exhaust their nuclear fuel, they don't fade quietly. They explode in supernovae, events so energetic they briefly outshine entire galaxies. The shockwave from these explosions tears through surrounding space, heating gas to millions of degrees and creating expanding shells of debris that glow for thousands of years. These are supernova remnants, and measuring their distances in light years reveals just how far-reaching these cataclysms truly are. Take the Crab Nebula, one of the most studied objects in astronomy. Located about 6,500 light-years away in the constellation Taurus, it's the expanding remains of a supernova that exploded in 1054. Chinese and Arab astronomers recorded seeing a guest star so bright it was visible during the day for 23 days and remained visible at night for nearly 2 years. That explosion happened 6,500 years before 1054, but the light only reached Earth in the Middle Ages. Today, the Crab Nebula spans about 11 light-years across and continues expanding at roughly 1,500 kilometers per second. At its heart sits a pulsar, a rapidly spinning neutron star, the compressed core of the star that exploded. This stellar corpse rotates 30 times per second, beaming radiation across space like a cosmic lighthouse. The Veil Nebula, another stunning supernova remnant, lies approximately 2,400 light-years away in the constellation Cygnus. It's part of a larger structure called the Cygnus Loop, the result of a star that exploded between 10,000 and 20,000 years ago. The Veil Nebula spans roughly 110 light-years across, a gossamer sheet of glowing gas rippling through space. When you look at images of the Veil Nebula, you're seeing the aftermath of stellar death, frozen in time by the light-year distance. The explosion happened millennia before human civilization arose, but we're only now receiving the light from those expanding shock fronts. These remnants teach us about the life cycles of stars and the enrichment of the galaxy with heavy elements. Every atom heavier than helium in your body was forged inside a star or during a supernova explosion. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it came from stars that lived, died, and scattered their enriched ashes across space. Those ashes condensed into new clouds of gas and dust, which collapsed to form new stars and planets, including our Sun and Earth. We are made of recycled stardust, the legacy of stellar explosions that occurred billions of years ago, light years away from where our planet would eventually form. Understanding light years also reveals the limitations and possibilities of future exploration. Scientists and engineers dream of interstellar missions, of sending probes or even crewed ships to other star systems, but the distances are staggering. Even our nearest stellar neighbor, Proxima Centauri, at 4.24 light-years, presents an almost insurmountable challenge. Conventional chemical rockets, the kind we use to launch satellites and send spacecraft to Mars, are hopelessly inadequate. They're far too slow and require far too much fuel. Breakthrough Starshot, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes a radical solution: ultra-lightweight probes equipped with reflective sails, accelerated by powerful ground-based lasers. The concept is elegant. Build a probe weighing just a few grams, attach a thin reflective sail, and then hit it with terawatts of laser power. The photons bouncing off the sail would push the probe to velocities approaching 20% of light speed. At that velocity, the probe could reach Alpha Centauri in roughly 20 years, far faster than any conventional spacecraft. The challenges are immense. Building lasers powerful enough to accelerate the probe requires technology we're only beginning to develop. The probe would need to survive the acceleration, navigate the journey without course corrections, and then transmit data back across 4 light-years of space using minuscule power sources. And even if everything worked perfectly, we wouldn't receive the first images and data until about 25 years after launch. A quarter-century wait for a glimpse of another star system. But compared to the tens of thousands of years required with current technology, 25 years sounds almost achievable. Other concepts explore different approaches. Nuclear pulse propulsion, where a spacecraft rides the shockwaves of controlled nuclear explosions, could theoretically reach speeds of several percent of light speed. Antimatter engines, if we could ever produce and store antimatter in meaningful quantities, would offer unparalleled energy density. Generation ships, massive vessels designed to support human populations across centuries-long voyages, appear in countless science fiction stories and remain a theoretical possibility, though building one would require resources and coordination beyond anything humanity has achieved. Each of these concepts confronts the same barrier, the light year. No matter how clever the engineering, no matter how exotic the propulsion system, the distances between stars impose minimum travel times measured in years, decades, or centuries. Light itself takes years to cross these gaps, and nothing can go faster. This is the universe we inhabit, vast, ancient, beautiful, and profoundly separating. Yet there's something inspiring about this separation. It forces us to think long-term, to plan across generations, to consider legacies that extend far beyond individual lifetimes. An interstellar mission wouldn't just be a scientific endeavor, it would be a statement of hope, a declaration that humanity looks beyond immediate concerns and reaches toward the stars, even knowing we might not live to see the results. The scientists who design the mission, the engineers who build the spacecraft, the public who funds it, none of them might witness the probe's arrival, but their children or grandchildren might. And that distant future generation would inherit the gift of knowledge from another star system, a treasure earned through patience and persistence. The light year helps us understand phenomena that bend our intuitions about reality itself. Take gravitational lensing, an effect predicted by Einstein's general theory of relativity. Massive objects like galaxies or galaxy clusters warp the fabric of space-time around them. When light from a distant object passes near this massive foreground object, its path curves, following the warped space-time. From Earth, this creates distorted, magnified, or even multiple images of the background object. Sometimes, when the alignment is nearly perfect, gravitational lensing produces an Einstein ring, a circular or arc-shaped distortion of a distant galaxy's light wrapped around the lensing object. These rings can magnify distant galaxies that would otherwise be too faint to observe, effectively turning massive galaxy clusters into natural telescopes. Astronomers exploit this effect to study galaxies billions of light-years away that existed when the universe was young. The lensing galaxy might be a few billion light-years distant, while the lensed background galaxy could be 10 or 12 billion light-years away. Light from that distant galaxy, traveling for over 10 billion years, gets bent and amplified by a galaxy cluster it happens to pass, allowing us to peer deeper into cosmic history than our instruments could otherwise reach. This interplay of distances measured in light-years reveals the layered structure of the universe. Foreground, middle ground, and background objects, separated by billions of light-years of space, interact through gravity and light, creating cosmic alignments that we can observe and study. Each photon carries information not just about its source, but about everything it encountered along its journey. Light passing through clouds of gas picks up absorption lines, dark bands in the spectrum corresponding to elements in those clouds. By analyzing these spectral fingerprints, astronomers reconstruct the conditions light traveled through across billions of light-years. Now let's talk about quasars, among the most luminous and distant objects we can observe. Quasars are supermassive black holes at the centers of galaxies, surrounded by accretion disks of superheated gas and dust spiraling inward. As matter falls toward the black hole, it heats to millions of degrees, radiating enormous amounts of energy across the electromagnetic spectrum. A single quasar can outshine an entire galaxy containing hundreds of billions of stars. These cosmic beacons can be detected from billions of light-years away, making them invaluable tools for studying the early universe. The most distant quasars observed lie over 13 billion light-years from Earth. We're seeing them as they appeared less than 1 billion years after the Big Bang. These ancient quasars tell us that supermassive black holes, some containing billions of solar masses, already existed when the universe was young. This presents a puzzle. How did black holes grow so massive so quickly? The formation mechanisms and growth rates required to produce billion solar mass black holes in the first billion years challenge our models of black hole evolution. It's a mystery scientists are actively working to solve, using observations from Webb and other cutting-edge instruments. Quasar light that has traveled for 13 billion years carries stories from the universe's youth. By the time that light reaches our telescopes, it has been stretched by cosmic expansion, its wavelengths lengthened from ultraviolet and visible light into the infrared. This stretching, called redshift, is proportional to distance. The more distant an object, the faster it's receding due to cosmic expansion, and the more its light is redshifted. Astronomers use redshift as a proxy for distance. A quasar with a redshift of 7.5, for example, emitted its light when the universe was only about 700 million years old. That light has been traveling for over 13 billion years, crossing incomprehensible distances measured in billions of light years. The light year anchors our understanding of cosmic evolution. By looking at objects at different distances, we're essentially sampling different epochs of cosmic history. Nearby galaxies show us the universe as it is today, mature and structured. Galaxies a few billion light years away show us what galaxies looked like in the universe's middle age. Galaxies 10 or 12 billion light years away reveal younger, smaller, more chaotic structures from the era when galaxy formation was at its peak. And the most distant galaxies, over 13 billion light years away, show us the first generation of stars and galaxies emerging from the cosmic dark ages. This creates a kind of cosmic archaeology. We can't travel back in time, but we don't need to. The universe's finite light speed and vast distances mean that looking farther away is looking back in time. Every deep field image from Hubble or Webb is a window into the past, with the most distant objects representing the earliest chapters of cosmic history. The light year is both a spatial measurement and a temporal one. 4 billion light years away also means 4 billion years ago. Distance and time become intertwined, two aspects of the same cosmic dimension. Consider the cosmic web, the large-scale structure of the universe. Galaxies aren't distributed randomly. They cluster together along vast filaments, surrounding enormous voids where few galaxies exist. These filaments span hundreds of millions of light years, connecting clusters of galaxies in a network that resembles neural pathways or biological tissue. Mapping this structure requires measuring distances to thousands of galaxies, determining how far away each one lies in light years, and plotting their positions in three-dimensional space. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies out to distances of several billion light years, revealing this cosmic web in stunning detail. What we see is the result of tiny quantum fluctuations in the early universe, amplified by billions of years of gravitational attraction. Regions that were slightly denser pulled in more matter, growing into the galaxy clusters and filaments we observe today. Regions that were slightly less dense became voids, emptied as matter drained into surrounding overdense regions. The entire structure evolved over billions of years, driven by gravity acting across billions of light years of space. Understanding these structures helps cosmologists test models of dark matter and dark energy. Dark matter, which makes up about 27% of the universe's total mass energy, doesn't emit or absorb light, but its gravity influences how galaxies form and cluster. Dark energy, which comprises roughly 68% of the universe, drives the accelerating expansion of space itself. Both are invisible, detectable only through their effects on ordinary matter and light. By mapping how galaxies distribute across billions of light years and measuring how that distribution changes with distance, and therefore with time, scientists constrain the properties of dark matter and dark energy, two of the most profound mysteries in physics. The Hubble Ultra Deep Field, captured in 2004, exemplifies the power of the light year as a tool for cosmic exploration. Hubble stared at a tiny patch of seemingly empty sky, about 1/13 the diameter of the full moon, for over 11 days, collecting every photon it could. The resulting image revealed approximately 10,000 galaxies packed into that minuscule area. Some were relatively nearby, just millions of light years away. Others were over 12 billion light years distant, their light emitted when the universe was less than a billion years old. Every speck in that image is an entire galaxy. Billions of stars, potentially trillions of planets, whole cosmic ecosystems separated from us by unimaginable distances measured in billions of light years, and this was just one tiny patch of sky. Extrapolate across the entire celestial sphere, and the number of galaxies in the observable universe reaches into the hundreds of billions, perhaps even 2 trillion. Each one sits at a specific distance, measurable in light years, each one a timestamp from cosmic history. The ultra-deep field and similar observations fundamentally changed how we understand galaxy evolution. By sorting galaxies by distance, and therefore by age, astronomers traced how galactic structures changed over time. Young galaxies in the distant universe appear smaller, more irregular, and more actively forming stars compared to older, nearby galaxies, which tend to be larger, more structured, and less actively producing new stars. We're watching galaxies grow up across cosmic time, from small, chaotic clumps in the early universe to the majestic spirals and ellipticals we see today. But how do astronomers actually measure these distances? For nearby stars within a few hundred light-years, parallax works beautifully. Parallax measures the apparent shift in a star's position as Earth orbits the Sun. Observe a star in January, then again in July when Earth is on the opposite side of its orbit, and the star appears to shift slightly against the background of more distant stars. The amount of shift, measured in fractions of an arcsecond, inversely correlates to distance. A larger shift means the star is closer. A smaller shift means it's farther away. The European Space Agency's Gaia mission, launched in 2013, revolutionized parallax measurements. Gaia has measured the positions and distances of over 1.3 billion stars with unprecedented precision, creating a three-dimensional map of our galactic neighborhood. For stars within a few thousand light-years, Gaia provides distance measurements accurate to within a few percent. This data has transformed our understanding of the Milky Way's structure, revealing details about spiral arms, stellar streams from disrupted galaxies, and the motions of stars throughout the galaxy. Interestingly, professional astronomers often use a different unit than light-years for stellar distances: the parsec. 1 parsec equals about 3.26 light-years, or roughly 19 trillion miles. The name comes from parallax arc-second. A star exactly 1 parsec away exhibits a parallax shift of 1 arcsecond as Earth orbits the Sun. Parsecs simplify calculations in professional astronomy, but light-years remain more intuitive for public communication. Both measure the same thing: the vast distances between celestial objects. For objects beyond parallax range, astronomers climb the cosmic distance ladder. Each rung uses a different technique, calibrated against the previous rung. Cepheid variable stars, discovered by Henrietta Swan Leavitt in the early 20th century, pulsate with periods directly related to their intrinsic brightness. Measure how long it takes a Cepheid to complete one brightness cycle and you know how luminous it truly is. Compare that to how bright it appears and you can calculate distance. Cepheids can be seen in galaxies up to about 100 million light-years away, extending our reach far beyond parallax. For even greater distances, Type Ia supernovae serve as standard candles. These exploding white dwarf stars reach a consistent peak brightness, making them visible across billions of light-years. By comparing their apparent brightness to their known intrinsic brightness, astronomers determine how far away they are. Type Ia supernovae were instrumental in the late 1990s, discovery that the universe's expansion is accelerating, a finding that led to the concept of dark energy and earned the Nobel Prize in Physics in 2011. Each method has uncertainties, and those uncertainties propagate up the distance ladder. A small error in parallax measurements affects Cepheid calibrations, which affects supernova measurements, which affects our understanding of cosmic expansion. Astronomers continuously refine these techniques, using new observations to reduce uncertainties and improve the accuracy of distance measurements. The light year remains constant, but our ability to measure how many light years separate us from distant objects improves year by year. There's a philosophical dimension to the light year that's worth contemplating. When we say a galaxy is 10 billion light years away, we're making a statement about both space and time. That galaxy existed 10 billion years ago in the form we observe it. But where is it now? Has it merged with other galaxies? Has it drifted farther away due to cosmic expansion? We can't know. The information about its current state won't reach us for billions of years, traveling at light speed across the intervening distance. In a very real sense, that galaxy's present doesn't exist for us yet. We're limited to observing its past. This creates a curious situation. If we could somehow instantly teleport to that distant galaxy, we'd find it looking very different from the images we see through our telescopes. It would be older, more evolved, possibly transformed by mergers or other processes. Meanwhile, if an observer in that galaxy looked back toward the Milky Way, they'd see us as we were 10 billion years ago, long before our solar system even formed. They'd see a younger, smaller Milky Way, probably in the midst of active star formation, maybe even colliding with a smaller galaxy. Each civilization in the universe sees all others as they were, never as they are, separated by light years of space and aeons of time. This temporal disconnect becomes even more dramatic when we consider the most violent events in the cosmos. Gamma-ray bursts, or GRBs, are the most energetic electromagnetic events known. For a few seconds to a few minutes, a gamma-ray burst can outshine the entire rest of the universe in gamma rays. These cataclysms occur when massive stars collapse into black holes, or when neutron stars collide, unleashing jets of particles and radiation traveling at nearly the speed of light. When one of these jets happens to point toward Earth, we detect a gamma-ray burst, the brightest gamma-ray burst ever recorded, designated GRB 2210009A, was detected in October of 2022. It occurred approximately 2.4 billion light-years away and was so bright that it temporarily blinded most gamma-ray detectors in space. The burst released more energy in 10 minutes than our Sun will emit over its entire 10 billion-year lifetime. Imagine witnessing that event up close, though not too close, or you wouldn't survive. The sheer power released across billions of light-years of space is almost incomprehensible. Most long-duration gamma-ray bursts originate from the collapse of massive stars in distant galaxies, often billions of light-years away. Short-duration bursts, lasting less than 2 seconds, typically result from neutron star mergers. These collisions not only produce gamma rays but also gravitational waves, ripples in space-time that propagate at light speed. The LIGO and Virgo gravitational wave observatories have detected dozens of these mergers, opening an entirely new window into the universe. In August of 2017, LIGO and Virgo detected gravitational waves from a neutron star merger located about 130 million light-years away in the galaxy NGC 4993. Within 2 seconds, gamma-ray telescopes detected a short gamma-ray burst from the same location. For the first time, humanity observed a cosmic event through both gravitational waves and electromagnetic radiation. Telescopes around the world and in space immediately swung toward the source, capturing the kilonova, a glowing explosion powered by the radioactive decay of heavy elements forged in the merger. That observation confirmed that neutron star collisions are responsible for producing much of the gold, platinum, and other heavy elements in the universe. Think about the light from that kilonova. It traveled 130 million light-years to reach Earth. The merger happened 130 million years ago during the Cretaceous period, when dinosaurs still roamed our planet. The neutron stars spiraled toward each other, their orbits decaying over millions or billions of years, releasing gravitational waves that rippled outward through space. When they finally collided, the explosion sent light racing outward in all directions. That light crossed 130 million light-years of space, passing through intergalactic voids, skirting around galaxies, finally arriving at Earth in 2017 to be captured by our instruments. The gravitational waves from that merger arrived almost simultaneously with the light, confirming that gravity propagates at the speed of light, exactly as Einstein's general relativity predicts. Both the gravitational waves and the electromagnetic waves covered the same 130 million light-year distance at the same speed. This perfect synchronization provides powerful evidence for the fundamental nature of space-time and validates decades of theoretical predictions. As of early 2026, the LIGO-Virgo-Cagra collaboration has detected over 200 gravitational wave events during their fourth observing run. Most are black hole mergers, some involve neutron stars, and a few represent mysterious objects whose nature remains unclear. Each detection includes distance estimates, often measured in millions or billions of light years, calculated from the strength and characteristics of the gravitational wave signal. These measurements complement and cross-check electromagnetic distance measurements, providing independent confirmation of cosmic distances and helping refine our understanding of the expansion rate of the universe. The light year connects these diverse observations into a coherent picture. Whether we're detecting light, gravitational waves, or neutrinos, the distances these signals travel are measured in light years. They all propagate at the speed of light through space-time, connecting us to events that occurred in the distant past, across vast cosmic distances. Each signal carries information, tells a story about its source, and adds to our growing understanding of how the universe works. Now consider the ultimate horizon, the edge of the observable universe. Beyond about 46.5 billion light-years, we cannot see. Not because there's nothing there, but because light from those regions hasn't had time to reach us yet. The universe is only 13.8 billion years old. Light from the most distant regions has been traveling since shortly after the Big Bang, but cosmic expansion has stretched the distances, pushing those emitting regions far beyond their starting positions. The observable universe is a sphere centered on Earth, with a radius defined by light's travel time since the Big Bang, expanded by the universe's growth. But the universe almost certainly extends beyond this horizon. It might be vastly larger than what we can observe. It might even be infinite. We simply don't know. The light year defines what we can see, but it also defines what we cannot. Everything beyond that 46.5 billion light-year radius is for now, and perhaps forever, beyond our view. The information about those regions moves toward us at light speed, but the regions themselves are receding faster than light due to cosmic expansion. The horizon isn't fixed. It grows as the universe ages and more light reaches us, but it will never encompass everything. This creates a strange situation. Observers in distant galaxies, many billions of light-years away, have their own observable universes centered on their locations. Their horizons overlap with ours, but also extend into regions we cannot see. Each civilization in the universe, if they exist, inhabits their own observable bubble, defined by light-years of distance and billions of years of time. We're all isolated by the finite speed of light and the vast distances between us, each seeing a different slice of cosmic history. There's a melancholy beauty to this cosmic loneliness. We're surrounded by wonders, billions of galaxies, each containing billions of stars, each star potentially hosting planets, some of those planets perhaps harboring life. yet we're separated by distances so vast that communication, let alone travel, seems impossible. The light year quantifies this separation, makes it concrete, and in doing so, helps us appreciate both the grandeur of the cosmos and our place within it. But our isolation isn't permanent, at least not in our immediate cosmic neighborhood. While we're separated from most of the universe by billions of light years, we're actually on a collision course with our nearest large galactic neighbor. The Andromeda Galaxy, also known as M31, lies approximately 2.5 million light-years away. It's approaching us at about 110 kilometers per second. In roughly 4 to 5 billion years, though recent studies in 2025 suggest there's now only about a 50% chance of this happening, the Milky Way and Andromeda may collide and merge. This sounds catastrophic, but galactic collisions are surprisingly gentle affairs for individual stars. Galaxies are mostly empty space. The distances between stars within a galaxy are so vast that during a galactic merger, the probability of two stars actually colliding is negligibly small. Instead, the galaxies pass through each other like ghosts, their stars redistributing as gravity reshapes both structures. Over billions of years, the two spirals would merge into a single elliptical galaxy, sometimes nicknamed Milkomeda by astronomers. The uncertainty about whether this collision will actually occur comes from new measurements of the motions of other nearby galaxies, particularly M33 and the Large Magellanic Cloud. These galaxies influence the orbits of the Milky Way and Andromeda. Depending on their exact masses and velocities, which remain somewhat uncertain, they could either increase or decrease the likelihood of a merger. The Large Magellanic Cloud's orbit in particular runs perpendicular to the Milky Way-Andromeda trajectory, and its gravitational influence might deflect Andromeda just enough for the two galaxies to narrowly miss each other. Even if they do collide, the event won't happen for billions of years. That's billions of light-years worth of time if we could measure time in space units, which is a strange way to think about it, but illustrates how intertwined space and time truly are. By the time this collision occurs, if it occurs, our Sun will have exhausted its hydrogen fuel and begun swelling into a red giant, engulfing Mercury, Venus, and possibly Earth. Life on our planet, if any remains, will have long since relocated or perished. The merger of our galaxy with Andromeda might be spectacular to observe, but there likely won't be anyone on Earth to see it. The future of the universe itself is tied to the light year in profound ways. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating. Galaxies far away, billions of light-years distant, are receding faster than closer galaxies, and the rate of recession is increasing. This implies the existence of dark energy, a mysterious force that permeates space and drives acceleration. Dark energy constitutes about 68% of the universe's total mass energy content, yet we don't know what it is. It might be a property of space itself, a cosmological constant that Einstein once proposed and later retracted. Or it might be something more exotic, a dynamic field that changes over time. Interestingly, recent studies from 2025 have raised intriguing questions about whether dark energy might be weakening over time. Some analyses of enormous cosmic surveys suggest the universe's expansion might even be beginning to slow down again, though this remains highly controversial and requires further verification. If true, it would revolutionize cosmology and our understanding of the universe's ultimate fate. But whether dark energy is constant or evolving, its effects will shape the cosmos across timescales measured in trillions of years. If dark energy remains constant and continues driving acceleration, the universe faces a cold, lonely future. Galaxies will drift farther and farther apart. Eventually, billions of years from now, galaxies beyond our local cluster will recede so fast that their light can no longer reach us. The observable universe will shrink, not because space is contracting, but because expansion carries distant regions away faster than light can travel. Future astronomers, if they exist, living in galaxies trillions of years from now, will look out and see a nearly empty sky. The cosmic microwave background will have redshifted into undetectability. Evidence of the Big Bang will have faded beyond observation. They might not even realize they live in an expanding universe born from a hot, dense beginning. This scenario, sometimes called the Big Freeze or heat death, results in a universe where stars eventually burn out, black holes slowly evaporate via Hawking radiation, and after unimaginable timescales, only cold, dilute remnants of matter and energy drift through ever-expanding space. The light year loses meaning in such a universe. There's nothing to see, nothing to measure, no light traveling between objects because all objects are too far apart, receding too fast, isolated by the cosmic expansion that never stops. Alternatively, if dark energy weakens or changes behavior, the universe might face different fates. It could slow its expansion, perhaps even reversing into a big crunch, where gravity eventually overcomes expansion and everything collapses back into a singularity. Or the universe might experience a big rip, where dark energy strengthens over time, accelerating expansion to such extreme rates that it eventually tears apart galaxies, stars, planets, and even atoms. Each scenario is speculative, dependent on the nature of dark energy, which remains one of the deepest mysteries in physics. But regardless of which future awaits, the light year will remain a fundamental measure for as long as light travels through space and observers exist to measure it. It's a unit born from human curiosity, our need to comprehend the cosmos, and our recognition that the universe operates on scales far beyond our everyday experience. The light year bridges the gap between the familiar and the incomprehensible, between human lifespans and cosmic timescales, between our tiny planet and the vast universe that surrounds us. There's something profoundly humbling about the light year. It reminds us that we are small, that our planet orbits an ordinary star in an unremarkable region of a typical galaxy among hundreds of billions of galaxies scattered across an almost unimaginably vast universe. And yet, paradoxically, it also reminds us that we are capable of understanding this vastness. We've measured distances across billions of light years. We've traced the history of the cosmos back to its first moments. We've discovered planets around distant stars, detected gravitational waves from colliding black holes, and mapped the large-scale structure of the universe itself. The light year is more than a unit of measurement. It's a testament to human ingenuity and persistence. When ancient astronomers first looked up at the stars, they had no concept of how far away those points of light truly were. Some thought they were holes in a celestial sphere through which heavenly fire shone. Others believed they were gods or spirits watching over humanity. The idea that stars were distant suns, that light had a finite speed, that we could measure cosmic distances, all of this developed gradually through millennia of observation, experimentation, and theoretical insight. Old Romer's 1776 observation of Jupiter's moons provided the first evidence that light travels at finite speed. Astronomers measuring stellar parallax in the 1830s confirmed that stars lie at enormous distances, far beyond anything previously imagined. Einstein's theories of relativity in the early 20th century revealed that light speed is the ultimate speed limit, woven into the fabric of space-time itself. Each discovery built upon previous work, each generation of scientists adding to humanity's collective understanding. Today, we stand at an extraordinary moment in history. Our telescopes peer back to within a few 100 million years of the Big Bang, Our instruments detect phenomena our ancestors couldn't have dreamed of: black holes, neutron stars, dark matter, dark energy, exoplanets, gravitational waves. We've sent spacecraft to every planet in our solar system and beyond. We've even sent 4 probes, Pioneer 10 and 11 and Voyager 1 and 2, into interstellar space, though they'll take tens of thousands of years to cover even a single light year of distance. The Voyager probes, launched in 1977, are now over 22 billion kilometers from Earth, about 150 times the Earth-Sun distance. That sounds impressive until you realize they've covered less than 0.003 light-years in nearly 50 years of travel. At their current speeds, they'll need roughly 17,000 years to travel 1 light-year. And they're not headed toward any particular star. They're just drifting outward, silent ambassadors carrying golden records with sounds and images from Earth, messages in bottles cast into the cosmic ocean. Those golden records represent a beautiful hope that someday, somehow, another intelligent species might find them and learn something about us. But the odds are astronomical. Space is vast, and the Voyager probes are tiny. They could drift for billions of years without encountering anything. The light year reminds us of this reality. It quantifies the emptiness, the distances, the challenges that make interstellar communication or travel so difficult, and yet we continue to search. The search for extraterrestrial intelligence, SETI, scans the skies for radio signals from other civilizations. So far, after decades of searching, we've heard nothing but cosmic static. This silence might mean we're alone. It might mean other civilizations are too far away, their signals too weak or pointed in other directions. It might mean intelligence is rare, or that civilizations inevitably destroy themselves before achieving interstellar communication, or it might simply mean we haven't searched long enough, haven't looked in the right places, haven't recognized signals for what they are. If we ever do detect a signal from another civilization, the light year will immediately become relevant in a new way. How far away are they? If the signal originated from a star 100 light-years away, we're hearing a message sent a century ago. Our reply, traveling at light speed, won't arrive for another century. The conversation would take 200 years for a single exchange. Any civilization we communicate with would need to be extraordinarily patient and long-lived, or willing to engage in multi-generational dialogue. This constraint shapes science fiction stories about first contact, but it's a real physical limitation. Unless we discover something fundamentally new about physics, something that allows faster-than-light communication, which all current evidence suggests is impossible, then conversations with distant civilizations will always be slow, measured in decades or centuries for each exchange. The light year separates us not just spatially but temporally, creating barriers that technology might never overcome. Despite these limitations, the search for knowledge continues. New telescopes come online, new missions launch. Scientists propose ever more ambitious projects: gravitational wave observatories in space, neutrino telescopes deep underground or under polar ice, interferometers spanning entire continents or operating in deep space. Each instrument extends our reach, allowing us to observe fainter, more distant, more ancient objects. Each discovery measured in light years adds to our cosmic story. And that story is magnificent. We've learned that the universe began in a hot, dense state 13.8 billion years ago. We've watched it expand and cool, forming the first atoms, the first stars, the first galaxies. We've traced cosmic evolution through billions of years, seeing galaxies merge and grow, stars live and die, heavy elements spread through space. We've discovered that planets are common, that the ingredients for life exist throughout the cosmos, that the universe is far stranger and more wonderful than anyone imagined. The light year has been our guide through this journey. It's helped us map the cosmos, understand its scale, and place ourselves within it. When we say the Andromeda Galaxy is 2.5 million light-years away, we're connecting ourselves to that galaxy across space and time. When we observe light from galaxies 13 billion light-years distant, we're witnessing cosmic history, seeing the universe as it was when it was young. The light year makes these connections tangible and comprehensible. Looking forward, future generations will continue this work. They'll build more powerful telescopes, develop new detection methods, and push the boundaries of what we can observe. Perhaps they'll detect biosignatures in the atmospheres of exoplanets dozens or hundreds of light-years away, finding evidence of life beyond Earth. Perhaps they'll map the cosmic web out to even greater distances, revealing new insights about dark matter and dark energy. Perhaps they'll detect gravitational waves from the Big Bang itself, opening a window to the first moments of cosmic history. Or perhaps they'll make discoveries we can't yet imagine, finding phenomena that revolutionize our understanding of physics and the cosmos. History suggests that each generation's certainties become the next generation's antiquated ideas. We once thought Earth was the center of the universe. We once thought the Milky Way was the entire cosmos. We once thought the universe was static and eternal. Each of these ideas fell as observations revealed deeper truths. What current ideas will future discoveries overturn? Whatever comes, the light year will remain. As long as light travels through space, as long as we observe distant objects, we'll need units to measure those distances. The light year, elegant and intuitive, connecting space and time through the fundamental constant of light speed, will continue serving as our cosmic yardstick. It's a small piece of human culture that bridges the finite and the infinite, the momentary and the eternal, the human and the cosmic. So when you look up at the night sky and see stars twinkling in the darkness, remember, each point of light has traveled for years, decades, centuries, or millennia. To reach your eyes, you're seeing ancient history, light from stars as they were long ago. And when you contemplate the distances involved, measured in light years, remember that you're connected to those distant suns through the same physics that governs everything in the universe. The light that entered your eye was emitted by nuclear fusion in a stellar core light years away, traveled across the void, passed through Earth's atmosphere, and triggered chemical reactions in your retina, allowing you to perceive and wonder. That's the gift of the light year. It connects us to the cosmos while reminding us of our place within it. We're made of stardust, living on a small world orbiting an average star in a typical galaxy among hundreds of billions, spread across billions of light-years of space, and yet we're capable of understanding all of this, of measuring the immeasurable, of comprehending the incomprehensible. The light year is both a measure of distance and a measure of human achievement, a reminder that while we may be small, our curiosity, our intellect, and our determination to understand the universe are anything but. And so the story continues, measured one light year at a time, stretching from our small world to the farthest reaches of the observable universe, connecting past, present, and future in a grand cosmic narrative that we're privileged to read and help write. If you made this far, I am sure you will love this other video at the left side of the screen. Why is light speed the limit? What Feynman uncovered will melt your mind. Discover what Richard Feynman found out about the terrifying truth of space-time and causality. See you there.